So we will go to the proof of this theorem. Under what conditions a level curve can be parametrized? So the theorem we have already stated. Proof. It's a geometrical proof, and it uses one Taylor's theorem for two variables and two inverse function theorem, I of t, inverse function theorem. So I'll draw a figure. Suppose that this is the level curve C. You have the coordinate axis, x-axis, y-axis. Here is the point P, x0, y0, and I want to parameterize this. So you choose another point Q, x0 plus delta x, comma y0 plus delta y, that lying on C. Q, x0 plus delta x, comma y0 plus delta y. So since P and Q both lie on C, you have f of x0 comma y0 equal to 0 and f of x0 plus delta x comma y0 plus delta y also equal to 0. And now you use Taylor's theorem for two variables. So f of x0 plus delta x comma y0 plus delta y equal to f of x0 comma y0 plus delta x into dou f by dou x plus delta y into dou f by dou y plus higher powers of delta x and delta y. Higher powers of delta x and delta y. Okay, when delta x and delta y are small, higher powers of delta x and delta y, they are going to be still smaller, so you can neglect this part. So let me remove this part. Okay. My axis, that also got removed. This is x-axis. This is y-axis. But this is equal to 0. This is also equal to 0. So this part, delta x into dou f by dou x plus delta y into dou f by dou y must be equal to 0. Equal to 0. This means that the vector dou f by dou x comma dou f by dou y which is precisely your del f, gradient of f, inner product with delta x comma delta y equal to 0. So this means that the vector del f is perpendicular to this vector delta x comma delta y. So what is the vector delta x comma delta y? It is this vector. And so this is perpendicular to this vector. Del f is perpendicular to this vector. So del f is like this. This is your del f, which is dou f by dou x comma dou f by dou y. Now when delta x and delta y are smaller, this line, this secant is nearly a tangent to the curve at the point P. Therefore del f is going to be normal at the point P, perpendicular to the tangent at P. So now our assumption is this is non-zero. This vector is non-zero. That means either this is not equal to 0 or this is not equal to 0. So let us assume that dou f by dou y is non-zero. Let us assume without loss of generality that dou f by dou y is non-zero. Assume dou f by dou y is non-zero. Second coordinate equal to 0 means you have a line parallel to or a vector parallel to the x-axis, because the equation of the x-axis is x comma 0. So second coordinate equal to 0 means you have a vector parallel to the x-axis. So second coordinate not equal to 0 means you have a vector not parallel to the x-axis. That means this vector delta x comma delta y is not parallel to the y-axis. So this implies delta x comma delta y, or the tangent vector. This is approximately the tangent vector. At the point P is not parallel to the y-axis. So this is a typical figure. This tangent vector is not parallel to y-axis. So this is the point x naught. This is the point y naught. So for each point x near x naught, you draw a line parallel to the y-axis that will meet the curve at some other point y, I mean x comma y. So you can have y here. If x happens to be here, x comma y will be here. This is your x comma y, and your y will be here. So for each x near x naught, so for each x near x naught, there is a unique y. unique y such that the point x comma y lies on the curve C, or in other words, f of x comma y is equal to 0. Okay? So this correspondence, getting y from this x, it is denoted as a function. It is going to be denoted as a function as follows. So put y is equal to g of x for each x near x naught. For each x near x naught. Therefore, I am going to look at a parameterization gamma of t equal to I will put x equal to t and y is equal to g of t, and you can show that this g is smooth. You can show that g is smooth. That uses inverse function theorem. G is smooth using inverse function theorem. So this is now what about gamma of 0? Gamma of 0 is 0 comma g of 0. So when t is equal to 0, your curve this is not very much required because if the interval does not contain 0, you can translate that interval appropriately. Now why this gamma is regular? Because if you differentiate this, gamma dot t equal to 1 comma g dot of t, that means dg by dt, and this is non-zero. So there exists a regular curve. This gamma is going to be regular because derivative is non-zero, and this is going to be a parameterization of part of C containing the point P. Gamma is a parameterization of part of C containing P. So this completes the proof of this theorem. This proof is a little bit geometrical, and its analytical proof is there that we will be discussing afterwards. Thank you.